applications. So this semester, previously we have the engine, state time and evening time, right? Okay. So this semester, since daytime students have other entries, so that the registration for the daytime BNG is very limited, then the daytime module has to be cancelled because of the low registration. However, our evening night class so welcome by students, right? Okay, more than 60 students, 66 students. Okay. On the other hand, how that will affect us, right? So originally we have the combined final exam, right? Okay. If you look at the past year paper, okay. So one paper for both daytime and night class, okay? So then, I guess this semester, the exam paper is only for night class, okay? So originally, you could have more choices, okay? Anyway, we will follow our original. Actually, previously also you choose, I guess, 2 questions from part A and 2 questions from part B, right? Okay. So I guess finally we will have maybe 4 questions. So you have to answer all 4 questions, right? Okay. Anyway, so previously although we have 8 questions, right? Actually, the 4 questions, another 4 is definitely for daytime. Another 4 questions are set for night class. Okay. So anyway, welcome to our class. We are very happy to have so many students. Okay. Compare with the BNG student, right? BNG student registration is very limited, so that department has to cancel, right? Okay. Anyway, now let's come back to this class. Okay. So since most or all of you have learned EE4101E, right? Also, we have taught the transmission line equation. So we will quickly go through this part. This chapter is actually section of number element model and the transmission line equation or telegraph equation, right? Okay. I hope you can still remember a little bit about this transmission line, right? Okay. So the basic idea for microwave engineering or big difference RF communications compared with low frequency electronics. Okay. The big difference is here. So for low frequency electronics, the voltage at here, the voltage at this location. Okay, voltage at this location, right, is equal to the voltage at the location B, right? Okay. Also, the current at the voltage at this location, right? Current IA is equal to IB, right? Okay. In your mind, what do you have in your mind in this? However, so that assumption is this physical length, for instance, the power line, right? The power line. What is the operation frequency for power line? For instance, in Singapore, it's 50 hertz, right? 50 hertz. 50 hertz. What is the corresponding wavelength. Wavelength is C over F, right? C over F. Then actually in the last class, in the last session, we have already mentioned this is actually 6 times 10 to 6 meter, right? This is 8, this is a 50, right? Okay. So it turns out this lambda is 6 times 10 to 6 meter. Okay. This physical length, for instance, 1 meter, 10 meter, or 100 meter, compared with this wavelength, physical length, compared with this, is very, very small, right? Okay? So means here, the phase delay is very, can be neglected, right? Negative, right? Okay? However, at IF microwave frequency, the lambda is, or the physical length is comparable with lambda. Okay. For instance, in the last session, I mentioned already or not? Anyway, for instance, Wi-Fi frequency 2.4 or 2.5 gigahertz, right? Or 1 gigahertz. Okay, 2.5 gigahertz. 2.5 gigahertz or 5 gigahertz Wi-Fi frequency, right? Okay. For instance, we use 5 gigahertz. Then what is the wavelength? Is C over 8. Okay, right? Then this is 3 times 10 to 8. Then this F is 5 times 10 to 9, right? Okay. So it's then the wavelength is 60 meter, right? Sorry, 60 millimeter, right? Okay. The wavelength is 60 millimeter or 5 gigahertz, right? Then this physical length, for instance, half meter or 1 meter is comparable, right? Comparable with wavelength. For instance, this is 30 millimeter is 30 millimeter. Then is half wavelength. 15 millimeter. Then is quarter wavelength. Half wavelength or quarter wavelength. Half wavelength means okay. On the other hand, we understand this waveform is this is one period, right? Experience 360 degrees. This is also corresponding to so-called one wavelength, one period, right? Okay. Then half wavelength means 180 degrees. 90 degrees corresponding to this quarter wave change, right? Okay. For instance, then the wave could change from 0 to peak, okay, with quarter wavelength phase delay, okay, or the peak become 0 with quarter wavelength, right? Okay. With half wavelength, could be positive peak become negative peak. This is for IF communication, radio frequency engineering, IF engineering, right? Okay. This is a big difference between the IF engineering or IF communications compared with what you have learned before or what you have in your mind is low frequency electronics. So low frequency electronics, the so-called lambda element model. Lambda element model is KVL and KZL. KVL and KZL. Okay? So assume the voltage and the current are the same along the transmission line, right? Okay? Along the transmission line. So now for RF microwave applications, because of phase delay, the voltage at this location is not equal to the quantity at this location, right? Okay, this voltage at this is not equal to this, current also is not equal, right? This is the difference because of the phase delay. For RF microwave engineering, this phase delay cannot be ignored. However, for low frequency electronics, this can be ignored, right? Can be ignored. Okay. So now then for RF microwave transmission line, then how the KVL, let's review the KVL and the KCL. So what does KVL tell us? Means the voltage drop, for instance, along this, right, is equal to this. Or directly the voltage drop along this loop is equal to 0, right? Okay? Right? KVL. KCL means incoming current is equal to outgoing current, right? Incoming current is equal to, for any load. This is for any load. What do you have learned in your low frequency electronics? KVL, this is KVL, this is KCL, okay? Bear in mind, this is assume physical length is much smaller than wavelengths, right? Much smaller than wavelengths, okay? So for microwave electronics, we still want to use this KVL and KCL. Then how can we use this? Okay, actually in our EE4101, we have already mentioned, right? Okay, now let's review this part. For instance, now we are handling a transmission line. Okay, transmission line. Typically we use twin line to represent transmission line. Okay, also you need to understand. Okay, in your mind, maybe for low frequency electronics, just use one wire, right, to represent the transmission line. Okay, however, for transmission line at microwave frequency, you must have the signal line and the ground, right? Okay, for low frequency, since the wavelength is very large, so actually, where is the for low frequency? Where is actually also we need to have this ground plane, right? Our Earth in the ground plane or infinity in the ground plane, right? For low frequency electronics. Maybe you don't realize. However, the ground plane, exists, right? For microwave RF frequency, you must draw the ground plane. Okay, this ground plane is supposed to transmit signal, RF signal. Okay, so since now we have no idea whether this transmission line physical length is much smaller than wavelength, right? Typically going to be comparable. So you cannot directly apply the KVL and the KCL. So then how can we, then I would pose a question, can we still use KVL and the KCL to RF microwave transmission line? The answer is yes, we still can, but we need to do some further step before we apply the KVL and the KCL to transmission line. What we should do is we try to divide this transmission line into many small sections, right? Okay? For each section, suppose this physical length is much smaller than wavelength. Then we can apply the KVL and the KCL to this very short section of transmission line, right? Okay, then we cascade the multiple sections together, right? Okay, multiply multiple sections together, then we can understand we can characterize, understand the transmission line. That is what you have learned in EE4101E, right? Is engineering electromagnetics transmission line chapter. Right? Here we just review what we have learned. Okay, right? Then very famous RLGC, right? Very famous RLGC. Okay, RLGC. What do they represent? What do they represent? Who can answer? RLGC. Okay. Who can answer? Here we have the RLGC. Now for this transmission line, or for this section of transmission line, right? Okay. For this section of transmission line, what do RLGC represent? Okay. So, okay. Who can answer? R represents the conductor loss, right? R represents the conductor loss, okay? L means inductance of the transmission line, right? L means the, okay? So also you have learned in EE4101. Okay, the C means the capacitance. Okay, G means the maybe some substrate, then substrate loss, or the material loss. Okay, of the transmission line, or leakage, right? Okay, some kind of leakage. So then each section will resonate, since we have the L and the C. L and the C will form the resonance. Okay, each section will have resonance. This resonance, then signal can be transmitted from the left to the right side. Right? Okay. So all this you have learned before, then we will quickly go through, then we will more look at conclusion. So this is first order wave equation, right? So basically now voltage and current are coupled together. So you cannot solve this directly, solve this voltage and current directly. So what we can solve? We try to decouple the voltage and the current. So the idea is in one equation we only have one variable. Okay, then we can solve the equation, right? That is the idea. We have the second order wave equation. So also we ever introduce the phasor form. What is the phasor form? Okay, this is time domain. Sorry. This is time domain. This is this so-called phasor form. This is the frequency domain, right? Okay. Then the relationship is given by this. This is the time domain and phase domain, right? So also here, for instance, this is time domain. This is frequency domain. In frequency domain, you cannot see the omega t, right? Here, omega t is in time domain or in the instantaneous format. Frequency domain. The advantage or benefit by introducing the phasor form is derivative can become simpler. Okay, this is the idea. So for instance, the first order derivative with respect to t, then in the frequency domain, just the j omega. Okay, then the second order, then just j omega square. So this is the concept by introducing the phasor format. Since we have learned in EE4101, so this part I will go through very fast. Okay. So I hope you still can remember. Okay. Then from there, okay. So previously we mentioned that this is a first order wave equation, right, in time domain. Then by introducing the phasor format, this is first order. Now here, V is frequency domain, right? You cannot see the T, right? Okay. Okay. Then here also voltage and the current are captured, right? Then to solve that equation, so we have to convert to the second order wave equation. By second order wave equation, now you can see in this equation we only have one variable. Okay, voltage. This equation we only have one variable, is current, right? So then we can solve the voltage and the current. This is very important. This is the concept, right? In the whole idea how to solve the wave equation, right? Okay. Then this gamma is the propagation constant, has the real part and the imaginary part. Real part represent the attenuation. The imaginary part, beta, is the propagation constant. Propagation constant times the physical length represent the physical length or electrical length, right? Okay. Then the solution for the wave equation is incident wave. Incident wave plus reflected wave, right? Incident wave plus. This is the physical meaning of the solution, right? Similarly for the current, also physical incident plus reflective. Then from there, okay, we have defined, okay, after the manipulation, okay. Here, more important is characteristic impedance of transmission line, right? So in the last session, we mentioned the characteristic impedance of microchip line, right? Microchip line, okay? So what is the characteristic impedance? Okay, actually defined by this, okay? So then from here, for instance, now if is ideal transmission line, R equal to 0, G equal to 0, then the transmission line, the characteristic impedance, it will be defined by square root L over C, right? Means the characteristic impedance will not depend on the frequency, okay? Will not depend on the frequency for ideal, okay? A lossless transmission line, right? Okay? As mentioned, this is in frequency domain. Frequency domain. Yeah, definitely you can convert back to time domain. Right here, time domain with T. Right. This without a T means in frequency domain. This means in time domain. Right. In time domain, is the voltage with distance and time, right? What transmission line tell us, right? Will tell us the voltage and the current along transmission line with different location and the time, right? Okay. Then also, this is very classical. Also in EE4101 we mentioned this is a very classical engineering problem. Very classical engineering problem. One section of transmission line, right? One section of transmission line could be terminated by antenna, right? Then the left-hand side connected with a transmitter. This could be connected with a transmitter, okay? TX, right? Connected with this transmission line. Then this is antenna, right? Antenna. Then signal will be transmitted to free space outside. This is IF linear. I guess some of our students have been having we switch to work as IF linear. Bear in mind, this is very classical application, right? One section of transmission line connected with antenna, right? Left hand side is transmitter. Then as IF engineer, okay, or system engineer, okay, you need to estimate how much power can be transmitted to outside, how much power will be reflected, right? For instance, for defense application, also I mentioned big phase array antenna, then a small percentage of power will cause a lot of problem. So, for instance, also typically the currently still a lot of challenge for transmitter design. Typically the power amplifier, the last stage for transmitter, the efficiency is very low. Typically it could be less than for radar, for instance, for radar application. That's 30%. Okay, means 70% of the power will be converted to heat. Okay, huge amount of power. For instance, long distance radar or phase array antenna, then 10,000 elements. Okay, the power could be 1,000 kilowatt. Then 50% of the power, right? Then huge of power. Need a huge cooling system. Okay. So, for instance, for base station antenna design, also the typically base station, for instance, a rooftop base station for cellular phone. Without rooftop, I guess you have seen many rooftop antenna, right? Rooftop antenna. Okay. The transmit power is huge. So sometimes also we could base the transmitter station, right? Okay. Also the transmit power is very large. Typically, residents don't like those base stations, right? So that's why I put on the top of the building because the transmit power is very large. Okay. Try not to face anyway residential area. Okay. Anyway, with the base station, then you can receive the cellular phone signal, right? Okay. So for those, also need to design the IF system. Okay. So the idea is try to minimize the reflection. So the so-called impedance matching is very important. So in our following session for amplifier design, actually our task is to design the matching network. The input matching, output matching, right? Okay. So in many cases, so we need to design the matching network, right? Okay. So maybe some students in the following years could take the final year project, for instance, to design the antenna, design some other passive circuit. Also, majority of the task is to design the matching network, okay, to minimize the reflection, okay. So from here, since we mentioned how to characterize the reflection, this is very important. Very important. Reflection coefficient, right? Reflection coefficient. Load impedance. The difference between load impedance and characteristic impedance. The ratio of the difference and the sum, right? Okay. Then this is the so-called the reflection coefficient at the load. Reflection coefficient at any location along the transmission line is a complex number, right? Okay, is a complex number. Okay, it's defined by this equation, right? Okay. In the meantime, we also have another parameter. Okay, another parameter is SWR. right? It's SWR. What is SWR? It's standing wave ratio. Standing wave ratio, right? Standing wave ratio. If the transmission line does not have this termination, then in the transmission line is traveling wave, right? It's traveling wave. So with this termination, we have the incident. Also, we have the reflected. Then, with incident and the reflected, then we form the standing wave, right? Okay. I'm not sure whether you still remember. Anyway, I show you. So, let me show you. Okay, that this now like this is the traveling wave, right? Here is actually standing wave, will not move, right? Okay, maybe I try again. Initially is traveling wave, then with the reflected will form the standing wave. This is, for instance, this traveling, right? No reflection, right? Okay. Here is the boundary, incident and reflected will form the standing. Okay. So what does the SWR ratio? SWR is standing wave ratio. Actually, standing wave ratio is this maximum, this minimum. Okay, the ratio. Okay, is SWR. So in the meantime, we have learned this very famous transmission line equation, right? Transmission line equation. Here, the beta air. Beta is propagation constant, air is the physical length. Okay. This is very important, as I mentioned. It's 5-star important equation, transmission line equation. Right? Okay. Also, for some special case, we introduce the so-called quarter wavelength impedance transformer. Okay, quarter wave impedance transformer. For instance, this beta air is 90 degree. Then the tangent beta air is infinity, right? Is infinity. Okay, if beta air is 90 degree, right? 90 degree, then infinity. Some students mentioned we don't know how to handle this if this is infinity. Okay, if this is infinity, can we calculate the input impedance? Cannot. Right? Some students just play with the calculator, then totally this question has the error, right? Okay, right? Okay. So actually, compare with infinity, then the finite can be ignored, right? Can be ignored. So means this can be cancelled. This also. Okay, sorry. This still keep. We need to keep, right? We still need to keep this. Then this will be cancelled. Turns out is the air, right? Okay. So then the input impedance is Z0 squared divided by Z air, right? Okay. So this is then beta air 90 degree is so-called photo wavelength. Then this is very famous, so-called very famous application, photo wavelength transformer. Okay. The idea is, for instance, now the load impedance, right? Load impedance. For instance, this load is antenna, patch antenna. Then for instance, patch antenna input impedance is 100 ohm, right? The air is 100 ohm. Okay, 100 ohm. Then typically the typical transmission line. Typical transmission line 50 ohm. 50 ohm, right? 50 ohm. Okay. So 50 ohm. Then the impedance not match, right? Okay. So then you have to design the match network, right? Match network to minimize the reflection, Then we can design a match network. This quarter wavelength, right? Quarter wavelength. Okay. Means this you need to define the length of this transmission line, right? Also you define the line width. Okay. The line width is now from here. Input impedance, right? Now it's 50 ohm, right? 50 ohm. Okay. Then ZL is 100 ohm, right? Then you can define this Z0. Now Z0 is 50 times 100 is 77 ohm, right? So 77 by using the TX line, right? TX line, giving the microwave subject. Then you can design this. The length also is determined with quarter wavelength, right? Okay, quarter wavelength, right? Okay, so you as RF engineer, you have designed some circuit, right? Okay. So for some special case, short circuit, open circuit match load, you are aware, right? Okay, right? Still remember? Forgot? Okay. Okay. Anyway, so you need to review all this part, right? Since we have got previously, I think in the last semester, right? Okay. So short circuit, the load impedance means 0. Then for open circuit load is infinity. Match load means the load impedance is equal characteristic impedance. Then sum all this into this equation. Then you SWR reflection coefficient, right? SW this. Okay, right? Who can still remember? Can you still remember this? No? Okay. For those who got A minus and above, okay, in EE4101, still can memorize all this. Okay? No one can understand? Okay? I guess I believe some of you still can handle all this, right? Although they are quite, this is the tradition. Okay. Try to keep very low profile, right? Okay? Okay, then as also power flow is very important. Power flow, as mentioned for the typical transmission line problems, right? We need to understand how much power is reflected, how much power is transmitted, right? Okay, this is very this is very important. It's not only just an equation, right? Physical understanding, right? Okay, so by referring to a specific transmission line problem connected with antenna, the left side is a transmitter, right? Then, for instance, the transmitter power is 100 watt. Then reflecting coefficient is here, right? You can calculate. Then ask you to calculate how much power is transmitted to free space, right? Okay, this is the equation, right? Equation. Okay, so then from manipulation, so you can understand actually the average power along the transmission line can be represented by incident power and the reflective power. Okay, the reflection coefficient will be involved here, right? Will be involved here. Okay, right? Here is reflection coefficient square. Okay, then will represent power. Okay. Then this is very classic example is the transmission line, right? Transmission line, okay, right? This transmission line you can assume terminated by antenna. The antenna input impedance is this, right? This load impedance is this. For instance, this load is antenna, right? I'm not sure I have shown this. No. Wait. Okay, anyway, for instance, this antenna, right? Mobile phone antenna, very old mobile phone antenna, right? Okay, U-band antenna, right? Connected with transmitter, right? Connected with transmitter, okay? Then this is input impedance, for instance, this some feeding is here, okay? Some feeding is here, okay? Then this is one section transmission line, okay? Right. Then as you calculate the reflecting coefficient at this location, the SWR along the transmission line. Along the transmission line, actually SWR is the same at this location and this any location. If it is lossless transmission line, right? And the input impedance, looking to the right-hand side, right? Looking to the right-hand side, right? Okay, so this is quite straightforward. Loaded, the reflective coefficient and the load location, right? This just apply the equation, right? Then SWR, also by applying the equation, right? Also straightforward. Then when we ask to calculate the input impedance, just apply the transmission line equation, right? Transmission line equation, okay? The challenge part could be complex number calculation, although I mentioned many times, right? Some students still cannot handle. Oh, okay. Also in our module, in our following session, we will still need to handle the complex number calculation in the amplifier design. Anyway, you have to go through, right? To deal with the complex number calculation, right? Okay. So the good suggestion is practice more, right? To have more experience. To have that is not challenge. Okay. We try to reduce the load, right? Okay. Reduce your risk. Okay. The Smith chart. Okay, then we move on to the Smith chart, or should we have 10 minutes break? Break first, okay. Okay. Now it's 6:54. Okay, 20 minutes. So come back 7:15. Okay. Now some students may not have time to have the dinner. Okay, right? Okay.